Hi everyone, I'm gonna make a tutorial now on some basics of brain image processing using statistical parametric mapping. SPM is a tool freely available for MATLAB, and we're just gonna use some of its capabilities here. And we're gonna go through tissue segmentation from the brain. So we have the MRI T1 weighted, and we're going to segment into the different tissues in the brain, the gray matter, white matter, for example. And then we're also going to see how we can work together with two different image modalities that were acquired independently, in this case a PET image and an MRI, and then we can align them. And finally, we're also going to see how to bring everything into a common space, a common alignment. So in that way, we can compare directly different patients or healthy controls, different subjects. And I'm going to show you how to do that manually using SPM, but also I'm going to build a short script that you can use as an inspiration to build your own. And in that way we can automatize this whole process. Let's start by opening up SPM. So here is already installed and configured. That's pretty easy to find online on how to do. And we're gonna use the PET module. So we're gonna start doing segmentation of tissues. So despite that we open the PET module, we're gonna work on a MRI image right now. So we're going to create here, click on the segmentation. I'm already here. Don't need to worry for this specific case too much on these settings. What I'm going to show you is that we're going to use tissue probability maps for that, and we see we have the different classes 1, 2, 3, 4, 5, and 6. And you can read the details on your own time, but here it's going to lead to a gray matter, white matter, CSF, bone, and soft tissue maps for us here. So here on volumes we select. I'm already on my folder here of the example data. I'm going to get the example number 1. I'm going to select the MRI. You see that it appears down here. Done. And easy as that, we click play. We can see here on the main MATLAB window that things are running, and we can also follow the process advancing here. So now you can see that this is done here, and you can see that some files were created. So let me go to the data here. You can see this was just created, and we can visualize some of these images. So here is, for example, the defined MRI that we had beforehand, and let me get C1, which in this case is the gray matter. For example, C2, it's going to be white matter, C3, CSF, and you can rename them however you want. So now suppose that we want to do automatic process. We just come back here, we create a new batch. Remember that we didn't change any of the parameters. We just have now to leave this empty. And we can come here, click Save Batch and Script. Let me go one further. Here we create a folder called Scripts, and we can save this as segment, for example. Now that this is created, I'm actually not interested in this because we're going to be building our own routine to iterate through the subjects. So I can close this one. What I want to show you is this other one here on the folder that we just created. This segment job file is created together when we do save the batch file, and here is all the settings for the parameters, just like in the batch editor. And you can see on the first line it's undefined, so we can send automatically whatever we want. So from here, I'm just gonna quickly build with you. We can just list all the patients, and we can then start going through the subjects. So we start a loop, and then we have to get the specific ID of this subject we are currently working on, and then we can do the tissue segmentation, and we do then a similar approach, which you can do however it fits your liking best. So here we're gonna be listing all the files inside each of these folders, but we only want the MRI, so we look for the one that has MRI. But suppose that you already have a segmentation there or something like that, and the segmentation starts with a C in the file name, so we can also remove those from the folder, from this list. And now for the actual processing with SPM. So firstly, we need to initiate it, because suppose that we didn't before, because you can be running that without loading SPM in the beginning as I did before. And then this is again SPM jobman is the way to run any code, and then it's going 2 steps backwards and looking for that file we just created, and here is the input that we want. So this is, instead of clicking here and going and looking through it, we can just send it. So this is why we needed to select the proper MRI file. And then this is done for tissue segmentation. This is it. We can now save this here as, for example, auto processing, and don't forget to go back to this folder, because we are entering the folder of each subject when we do this, and then we can simply run it. Okay, great. Now that this is done, we have, as you can see here, the different tissue segmentations for all of our subjects. So now we can go to the next step. So suppose that I want to analyze together my MRI, my gray matter, for example, together with my PET image, but they were not acquired together. So that means that they are not aligned. And you can see that the brain on the anatomical image is not aligned with the brain in the functional image. So this is what we're going to fix now. We're going to bring the functional image into alignment with the anatomical image. To do that, we can come here on the register, co-register, estimate and reslice. And here we have to select a reference image and a source image. Reference image is the one that will be static, while the source image is the one that is moved about to match that one. So in this case, our reference image is our MRI, and our source image is the FDG PET image. And I would recommend using a trilinear interpolation in this case. So this is it. Now you click and you see it's going to start running here, and here you can follow the progress. Now this is done. And we can see here, for example, now we have a new file with an R in front. So this is how SPM works with the files. It adds a prefix every time it works in an image. And in this case, R means because it was realigned and resliced. And if we now take a look at the images as we did before, I can load up my original MRI and my realigned PET, and you see that now they are matching, and we can work with them together. So if we just make a contour here, for example, you can see that they are aligned. We can load up the gray matter, which is also aligned, and we can overlay both images together, and you see now you have the gray matter on the PET, and the PET I can actually put on colorful, and you can see now exactly the activity on gray matter. So to do that automatically, we just start with a blank batch editor. We can leave these spaces for the files empty, and yeah, don't forget to change here to trilinear. And now we go back as before, file, save, batch, and script. We go to our scripts here, and then we can call it register, for example. It's gonna create automatically this loop, which we're gonna dismiss it, but we can load the register underscore job file that was created, which has the settings that we are interested. You see the reference file is now undefined, the source file is undefined, and the interpolation is with the code 1, which is referent to the trilinear interpolation. And if we want, we can even change the prefix. I'm gonna leave it as R for now. So going back, we can actually use the same script as we had before. Well, we are not interested in doing the segmentation again for now, so we can just comment that out, and then we do a very similar thing for the co-registration. So we list we get all the files inside the patient's folder, but we have to make sure to select the PET image, and just in case we already have PET images that was registered beforehand, like I did manually now, but I'm just going to rewrite it for the sake of this tutorial, we're going to take the already registered one out of the list. And then it comes the SPM job file itself. We, using the SPM jobman function, we call our register underscore job.m, and then we have our reference image and the image to be aligned. Since we already had selected the EMR before, we can simply call it again. And now, if I run this, it should register the PET of all the subjects to the respective MRI. And you see, it's running. Since I commented out the segmentation, it's not going to do that right now, but we can have it there. And now we wait. We can even check how it's going here. So now that this is done, we can see here the new files we just created with the registered image. So we can work with the anatomical image, having some functional information together. Now, on the final part of this tutorial, we're going to go to what's perhaps one of the most important steps if you want to do a group analysis. So it's the spatial normalization. So it's the alignment between not two different modalities of the same subject, but between different brains, or different people. So suppose we want to compare voxel by voxel, pixel by pixel, the PET, for example, or the MRI, it doesn't matter, of one subject against the other subject. Obviously, they are not aligned because they were acquired independently, and this is very clear if I, for example, create this here and project to the other. Clearly, it's not aligned. So how do we deal with that? Is the spatial normalization. So in that way, we're going to have the images aligned to a common space. In this case, we're going to use the M&I space, and we can go here on this pre-processing section and that normalize batch. And now we have a series of options. Again, I'm already going to select the trilinear. You can select a different voxel size. A bounding box is essentially the size of the images, it's the volume which is to be written relative to the images, and here we double click on the data, and then we have the image to align is the image that is going to be used to calculate these transformations, these nonlinear transformations, so these warping and deformations of the specific brain into the common MRI space. And for that, it's better to have an anatomical image. So we're gonna go to our example data and we're gonna select our MRI. And the images to write is, these are the images that we want to have a final version saved in this common space, using the mathematical transformations that we just calculated for this MRI transformation. And because of that, all the images that are going to be written with this transformation, they have to be pre-aligned and pre-co-registered with the MRI. So this is why the previous step was important. So images to write, now we want, well, everything that we have here. So we want to have our MRI in the final space, all the different tissues, and also the PET, but it has to be the PET that we worked on, so the co-registered one, the one with the R in the beginning of the file. And then done, just checking, interpolation is trilinear, we click play, we see that it started running, and we can follow the progress here. And now we wait a little bit. So now that this is done, we can take a look at the resulting images, and if I open here the folder, you're gonna see these files with W, and these are the images that were transformed into this common space. And this one here, if I load it up, it contains the information about the transformation itself. And if I load it here, it's not gonna be much impressive because these images were already aligned beforehand. But if we now go into the automated process and process of the and also process the image of the other subject, we're gonna see something interesting. To do this automatically, we go as before. We select here empty batch. I'm gonna change here to trilinear interpolation, and here on data I'm gonna leave it open, and as before we're gonna save the batch and the script as we did here, and let's call it, for example, spat norm. So it's going to create this iteration, which we are not interested, but if we take a look here at the span norm job, we have the settings that we did. The interpolation is 1 because we want a trilinear interpolation. We have the volume that's going to be used for calculation of the transformations, and all the other ones who are going to be receive the mathematical transformation and going to be created a new file in MNI space. And you see it's a single input here, so you have to work with something now. And so for that, we already have here, we select all the files inside the folder. We want to have the PET that was registered to the MRI for transformation, and also all the tissues. This is what we have here. And then we create a single list of files that we want to transform, because as I showed before, as I can show here again, there's only one entry here. So I create a little list with all the files that I want to be transformed, and you can do that however you want. This, I think it's pretty clear for this tutorial. And we want the MRI itself, we want the PET, and the realigned PET, and also all the MR tissues. And then after all the files are selected, we again use the SPM jobman, you run, select our script, our reference file that will be used to calculate all the deformations to MNI space and all the files we want written in MNI space. So now to run the spatial normalization, I just cleared up the files a little bit, and we can just should be able to run it. Now that this is done, we can take a look at our final images. And you can see here we have the images with W. Let me get, for example, the PET of subject 1, and for example 2, let me get the PET 2. And you see, now they are perfectly aligned. And now we can even take the difference between the two images and see where the uptake was higher in one of the subjects than on the other, comparing voxel by voxel. Here is how our simplistic script looks like. We just start clearing everything, and we go to the subjects, and we can just clear everything. And just to show that it would work just fine, I can clear up this all these files, and restart again with my original files only. So you see here, this is where we started. If I clear everything, everything is uncommented. We can simply run it, and now by the end of this, we're gonna have the images realigned, segmented as we want. I hope that this is helpful for you, and good luck with your work.